Hello and welcome to this virtual global Azure presentation on Azure Functions, Event-Driven Compute on Demand. My name is Andrés Nava. A little bit about myself. I am currently a cloud solution architect and I have over 20 years of experience developing and architecting web applications, primarily on the Microsoft stack. In the past couple of years, my focus is on architecting for the cloud with an emphasis on Azure. However, I also have experience with AWS and GCP. Here's the agenda of what we'll cover today. We'll start off by talking about what are Azure Functions and how they fit in with other Azure services. We'll dig into event triggers, input and output bindings, and we'll see how they simplify integration by abstracting away implementation details. Next, we'll create several functions, primarily in C#, and cover development, debugging, and deploying. And finally, we'll explain what is serverless and how Azure Functions can be used with this emerging compute style. So let's get into some of the benefits that Azure Functions provides. So the first one is that you pay only for the time that your code is running. This is very different than the previous approach where you paid when your code was hosted in the cloud. With this new approach, you're only paying when your function is actually executing. So if your function is not being called right now, you're actually not being billed for it. The second benefit is that you trust that Azure will scale as needed. You let it determine when to scale out to additional instances and when to scale back in. There's no need for you to have to go in and configure scaling yourself. The third one is that you can easily run small pieces of code or functions in the cloud rather than having to worry about the whole application. This is very much in line with the microservices approach of development. And fourth, you can focus on the code to solve the problem at hand or at business value and not have to worry about the underlying infrastructure that runs it. In short, I think functions are the easiest way to get started with writing code on Azure. Now, let's talk about a little bit more detail as to the actual features that are provided by Azure Functions. So the first one is the choice of languages. Azure Functions allows you to program in any number of languages that it supports. So this way you can choose which languages are best for the solution, whether they are based on languages that you're most comfortable with, or perhaps there's a specific library that you would like to use that's only available in a specific language. So Azure Functions allows you to choose from any variety of languages that it supports. The second one is the simplified integration, and this is where triggers and input and output bindings come into play. This allows you to easily integrate with Azure services as well as third-party services in a seamless way where you don't have to learn new SDKs or any of the intricate integration code that you would have to create yourself. And like I mentioned, it is pay per use. So you only pay for when your functions are actually executing. And this one, I actually like to put it as a feature, the fact that just like much of the things that are coming from Microsoft nowadays, this too is open source, and that would include the runtime, the scripting, the Visual Studio tooling, and the portal are all developed in the open on GitHub. Now, Azure Functions sits on top of App Service, and this is a platform as a service offering. And you're probably familiar with app services if you've done any sort of development with web apps, API apps, or mobile apps. And app services has been around for quite a number of years, so it has been battle tested, and it is something that has been proven. And by the sheer fact that Azure Functions was deployed on top of app services, it actually gained quite a bit of features out of the box. So these are all features that that team did not have to implement in order for them to get Azure Functions out. So we mentioned how Azure Functions is all about being event-driven and how triggers and bindings make the integration with other services a lot easier. So let's dig into that a little bit. So we start off by having a trigger. And a trigger is essentially any event that you want to subscribe to. This event could be in Azure or it could be an external service. When that event fires, it will then trigger your code to execute. when your code is executed, it also will pass along an input to that function. So let's say, for instance, that you've subscribed to a container, a storage container, so that whenever there is a new blob added to that container, your function will be executed. Okay, so that happens. But then the blob itself is passed in as a parameter to your function. Now, the nice thing about this input binding is that this blob input could actually be provided to you in any number of types. So for instance, if you like, you can actually get the blob's content as a string. If perhaps the content of that blob is a JSON object, then it actually can be deserialized into an object in your class, for instance. If you would rather work with streams or byte arrays, the content can be passed to you as one of those types. Or if for some reason you wanted to actually interact directly with the storage SDK, then the blob can be provided to you as a native blob type. Now, I've only talked about blobs themselves, but this actually applies to any of the numerous types that Azure Trigger supports. This is just one example. So now you have your function executing and you have the input. Then you go ahead and you start adding some business logic and do whatever you need to do. Once your function is done, you're most likely going to want to either return a result or store the results into something else. So that's where output bindings come into play. So let's say, for instance, that you do your business logic and you want to add an output to a different blob storage. So same thing here. You can go ahead and write your object that you have in memory in your code, and you can serialize that into blob storage. Once again, you don't have to worry at all about the storage SDK. You simply have your object, and when Azure Function sees that your function has ended, it will serialize that content into the blob. Now, you're actually not limited to one output. You actually can specify multiple outputs. So as far as the supported triggers and bindings, I've gone ahead and I've organized them into 4 separate categories. So the first one is storage. So here, your function will be triggered whenever there's a new item added to a particular storage. So that could be blob, table storage, or into the Cosmos DB. Then I have here messaging bus. So here, this is a traditional pub sub where a publisher will add a message to a broker, and then the broker will dispatch that message to any subscriber. So that includes Service Bus, Event Hub, Queue Storage, and IoT Hub. For the HTTP section, I have HTTP, which is just your standard REST endpoints, and then also webhooks. And then there's also Event Grid, which is essentially PubSub, but it's done over HTTP. And the final section that I have here is the miscellaneous. So the first two are actually not triggers. These are actually exclusively output bindings. So SendGrid output binding allows you to easily send out messages using SendGrid. And when I mean messages, I mean email messages. And then there's Twilio that allows you to send SMS text messages. The last item here is a timer trigger function. This is actually a trigger that allows you to run your function on a predetermined schedule. So we've talked about the triggers bindings. Now let's talk about the supported languages. Azure Functions can be developed in any of these languages. So to start off for .NET, there's support for both C# and F#. In Node, there's JavaScript and TypeScript. For Java, you can use Maven and Gradle, and I think this is Java version 8. For PowerShell, this is PowerShell Core, and Python, there's support for 3.6 up to 3.8. Now, when you deploy your Azure Functions, you actually have 3 hosting plans that you can choose from. So I'm only going to highlight 2 of these. However, the third one is essentially a blend of the 2. The first hosting plan is the App Service plan. Here is where you're able to select the amount of resources that your app service will receive. So you'll specify the compute and you specify the amount of memory that it will receive. And then when you're configuring this, you actually will see the predetermined price of what it will cost to run that function app in an app service plan for 1 month. Now here for scaling, it is up to you to determine how you would like to scale your function out when it needs additional instances or when it should scale back in to remove any extra capacity that it does not need. So here you would go in and you would specify a metric and a threshold. So for instance, a metric could be the CPU percentage. Let's say that you say that CPU, if it goes above the threshold of 70%, then you want to add an additional instance of your function app. Similarly, if you want to scale back in, you would also choose a metric and a threshold. So for instance, you could say that if the average CPU goes below 40% in the past 5 minutes, then go ahead and reduce the instance count by 1. Now, a quick thing to note here is that the minimum you can have with an app service plan is 1 instance of your function running at any time. So because this is more the traditional app service plan, you actually cannot go down to 0. Now, if we counter that with the hosting plan that was introduced when Azure Functions was released, this is the consumption plan. Here is a little bit different. Here is where you pay for only what you use. So the parts that I've been saying that you're only paying when your function is running, I was referring to your function being hosted in the consumption plan. As for scaling, you let you let the platform determine when to scale out and when to scale in. You actually do not have to go in and configure metrics or threshold. You just trust that Azure will know when to scale out and when to scale back in. And this is referred to as the dynamic plan and the serverless plan. And this plan can actually go down to 0. If Azure determines that there has not been any demand or any request for your function, it can actually be reduced down to 0. So this is where serverless comes into play. Now for the demo, I actually would like to put together a mocked processing pipeline. Essentially, we're going to be modeling an ordering system. So we'll start off by having an HTTP endpoint that will essentially be receiving orders. It'll receive an order in the payload. It'll do a little bit of business logic, and then it will add a message to a storage queue. Now, attached to that storage queue, we're going to have a queue triggered function, so that whenever there's a new message in that queue, the queue triggered function will be executed. That queue triggered function will then receive that order, and let's say that the business logic here is that it will generate a license key. And once it's done, it actually is going to write the output of that queue triggered function into a blob in a storage account. Now, what I would like to demo is the fact that the queue triggered function is only concerned when with the messages that are in the queue and actually has no visibility into the HTTP triggered function. So to showcase that, I'm actually going to go into the portal and I'm going to go into the queue and then add a message manually. So I'm not going to use a function to add a message to the queue. Instead, I'm just going to use the portal to add a message, which should also trigger the queue triggered function, and again, write that license file into the blob. So that is how things should play out. So now it's time for the demo. Here I am in the Azure portal, and what I'll do is I'll click on Create a Resource. Now I'm just going to walk you through the process of creating the function. I'm not actually going to create a function right now. I already have a function in place, but I would like to walk you through some of the options that you need to specify in order to create a function app. So we'll go ahead and search for a function app. This is the one that we want. Then we'll select a subscription, which already has the correct one. I currently have an existing resource group. I'll just select that, and I'll say that I want the global Azure Func. That'll be the name of my function app. It does have to be globally unique, and in our case, it is globally unique. So we'll continue. To publish, you have two options. You can either publish your code, or you can actually package your code into a Docker container. In our case, we'll just stick to code. Then we'll get the option to select which runtime stack we're going to be deploying on. In our case, it will be .NET Core. And the version, there's only one version supported here, and that's 3.1. For the region, I'll go ahead and I'll select West US 2. In hosting, we do need to specify a storage account. So for instance, I'll specify one that I already have. And then for the operating system, you have the option of either Linux or Windows. And then we get to the important section, which is the plan type. This is what will determine whether your function is serverless, whether you're using the premium SKU, or if you are on the traditional app service plan. For this, I would like to show you the app service plan, but this is, I'm not actually going to use it, so I'll just say delete me. This is what I would like to show you. If you are hosting your function on an app service plan, you would choose a actual app service plan, the size of the plan. So in this case, for instance, we have the standard S1 selected. With this plan, you get 100 total compute units and you get 1.75 gigs of memory. This is comparable to an A-series compute equivalent VM in Azure, and it will cost about $73 per month if we were to run an app service plan on this SKU. If that's not enough, we can actually jump up to an S2 where it would be double the compute, double the memory, and as you can see, also double the price. So the other option here though is that we would have auto scaling. So this is how we would determine how we go about scaling out to additional instances or scaling back in. So I'll go ahead and click on apply. Remember, we're not actually going to use this. I'm just walking you through these options. If I go to monitor, I would like to show you this application insight, how you go about integrating this. What you do is you just click on yes, and then it's going to, once you deploy your function, it's going to start profiling and capturing telemetry information and diagnostic information about your function when it's running. So those are the options that I just want to walk you through. Like I said, I'm not actually going to make use of this function app that we're creating. In fact, we're not going to create it. Instead, I already have one that's been created. So let me jump over to that. So here we have the HTTP triggered function. This is the first function that we had in our diagram. And what I'll do is I'm actually going to go into the integrate section so you can see the triggers and also the bindings. So first off, if we go into the triggers, we see that this is an HTTP triggered function. And this function responds only to select methods, not all methods. And those methods are get and post. Also, the HTTP request object is provided to us as an input to our function in the RAQ parameter. So now if we switch over back to our code, I would like to show you where that is. Here we have the HTTP request object, and that's our request itself. If I go back to integrate, then I go into the output section, I can see that there is one output for the HTTP, and that is being provided as a return value. If I take a look at the HTTP triggered function again, we see that indeed we have a return, which is of type action result, and this is an OK. So this would be a 200, and the body of that 200 would be the order, #, and then the order ID. Next, if we go back to the integrate, there is actually an additional output binding, and that is to an Azure Queue storage. The Azure Queue storage, we then have the configuration with the Azure Queue. So what we have here is we have this configuration saying that we will provide a value in a parameter in our function called output order. We want Azure Functions to then serialize that value into a queue as message into a queue named portal. So let's take a look at the code here. So here we have an out parameter, and it is of type order, and here is the definition of that type, and here's the actual parameter. So what it's going to do is it's going to take a look at what we provide as this value, and then it will take care of serializing that into a message in the queue. Okay, so I think at this point we have enough to walk us through this function here. Here, first off, we just do a simple log message. Next, we read the body of the request as a string, and then we deserialize that string into an order. So now the input is of type order, and it would have, in our test case, we're only going to be providing an order ID and a name. We're actually not going to be providing a date added. So with the business logic that we are mocking here is essentially we're just adding the value for date added as the current UTC time. What we're then doing is we're setting the output order to equal the input. And that's how we're able to provide the object that we want Azure Functions to serialize for us into a message in a storage queue. So to test this, I actually can go to the URL here, and I could do a post using like a Postman. However, Azure Functions does have an integrated test here. So what I'll do is I'll provide a JSON payload. And again, this is the object that we're passing in. So I'm going to mock that here. And I have an order ID of 1. And I'll say that the name is an HTTP triggered function. And then I'll go ahead and click on run. And as you can see, we have the output here saying that our function did indeed run. So the actual test to see if this worked is if we go to the queue and see if we actually have a new message. So I have that queue open in a different tab. And here we have the queue named portal. And if I were to refresh, we now have a message. Open that up, we can see that it's order ID 1 and the name is HTTP triggered function. So we do indeed have that message in our storage queue. So at this point, let's see if I can go back here. We are here. So next up, we're actually going to go and create a queue triggered function. We go back to the portal here. And so now here we have the queue triggered function. And I have this function currently disabled. And the reason that it's disabled is because this function is already wired up to listen to the queue. So if I were to go to the portal here, if I did not have that function disabled, it actually would have consumed this message and I would not have been able to show it to you. At this point, it actually has now consumed the message. The function was re-enabled, and since everything was wired up, it did process the message successfully. Okay, so now let's just go back and take a look at the integrate section. First off, we have a trigger. This is a queue triggered function. It is listening for messages in the portal queue. And it's going to be providing the message to the function in a parameter named called order. So let's go ahead and take a look at the function there. So we have a parameter named order, and it is of order type. So you saw how the message was serialized as JSON in the message. So now when this function is executed, that JSON message gets deserialized into this type. Next, we have the output. So this function is supposed to write a file as a blob into a container. So what this is going to do is it will have some kind of object in a license parameter, and it is going, in the Azure Functions, what it's going to do is it's going to get the content of this the value of this parameter, and it's going to serialize that into a blob in the licenses container and it's going to have a random GUID.txt. Now let's take a look at the code there. So here we have it will be a type stream, and the parameter is called license. And what it's going to do is it's going to create a license object. It's going to get the order ID, the name, and then it'll do a SHA-256 hash using the name and the order ID. It is going to serialize that object, and then it's going to get the byte array, and it will write those bytes into the stream. Now, if we were to, like I mentioned, this function already processed the message that was here. So this function has actually already executed once when it processed the message that was in the queue. What that means is that if we switch over to our storage container, and if we refresh, we should now have a licenses container, and inside that licenses container we now have a new blob. And if we open that up, we should see that we have the message here, order ID 1, name, and then the SHA. Okay, now if we go back and look at our code, we see that this is actually it's quite involved. This is a queue triggered function, so it's interacting with the storage queue, and then it's writing to the blob. So it actually does quite a bit. But if we take a look at the code here, there's nothing in here that talks about either of the SDKs. It does not make use of either of the SDKs. This is just standard C# code, but there's no mention of a queue in here, and there's no message of a blob. The only signs that there's possibly some kind of storage or anything like that would be just the fact that this is a stream, but there's no, this could have been written to local disk, it could have been written anywhere. It's all actually done through into the integration. This is where I was talking about, where it is the triggers and the input and the output bindings that take care of abstracting away all the integration, all those details that you don't have to know. So in this case, we were able to do all that without even having to know the intricacies of either of the SDKs. So I personally think that is one of the benefits of Azure Functions, is how it's able to abstract away a lot of those details. Okay, let's see. Now what I like to do is the fact that, let's see, so we're here right now, and next up I would like to go into the portal and write a message into the queue. So I am going back to this queue, which, remember, we have the function that is subscribed to this queue. Next, what I'll do is I'll add a new message. This one has an ID of 99, and it's a portal triggered function. So I just click on OK, and that adds a new message. If I refresh, notice that the message has been consumed. If I take a look at the function, you see the output, the fact that it is outputting the order ID, and that matches the 99. So if we go back into the licenses folder and I refresh, we now see the fact that we have 2, and I believe this is the most recent one, and it should have the 99. There it is. Okay, so notice that in this case, the queue triggered function knows nothing about either HTTP or the portal. Instead, all it's doing is just subscribing to the queue, to a storage queue, and whenever there's a new message, it would be executed. So this is a very nice way for us to decouple our application and have the HTTP triggered function know nothing about the queue triggered function, and vice versa. The last part here is the fact that in my case, I did integrate application insights. So what this is going to do is it's going to capture telemetry information about our function when it runs. So in this case, it's going to capture the dependencies. If I click on application map here, we should see how it was able to capture the fact that our function made a call out to the Azure queue and to the blob storage. So let's take a look at these calls here, and let's just click on one of those, and it just gives you some information about it's able to profile your application and see how it's behaving. And another thing here is the fact that if we go and look at our code, this too, there's nothing in here that integrates directly with application insights. There is an SDK if you would like to capture custom telemetry. However, as you can see here, there's nothing that we're doing where we're explicitly making use of that SDK. So there's another example where there's a lot of abstractions going on if you want to take advantage of those, and it's very simple to just turn those on. And that will conclude this demo of the Azure portal. Okay, now back to slides here. So what I've done here is I've demoed the Azure portal, and it's a very nice place to do demos. However, it's not really the place where, if you're going to production, that's probably not where you're going to be doing your development. Instead, most likely you're going to have a local environment that you're more comfortable with, where you have some pretty powerful tools. So Azure Functions does support local development, and it has support for Visual Studio. The earliest supported version of Visual Studio is Visual Studio 2017 Update 3. And if that's what you're running, then you would need to enable the Azure Development Workload, and you also need to install the Azure Functions extension. However, if you're in Visual Studio 2019, you actually just simply need to enable the Azure Development Workload. If you would rather do your development in Visual Studio Code, then all you need to do is add the Azure Functions extension from the extensions gallery. And once that's installed, then you can create a new function. The wizard will guide you by asking you to select the language for your functions. And once you select a function language, then you'll be prompted to select the trigger type. For this demo, we're actually going to be doing our development in Visual Studio 2019. So what I have here is Visual Studio 2019. I have a blank setup here. I'll click on Project, and I will type in function and select Azure Function here. Click on Next. Let's say this is our local function. And then I will specify that I want to choose a queue-triggered function. However, as you can see, you have a number of different triggers that you can choose from. And then, like I mentioned before, the Azure Functions requires a storage account. So the nice thing here is that I'm already logged into my Azure account. So I can go ahead and it will select the available storage accounts that I can select from. So I'll go ahead and choose that one. And then this is the name of the connection string setting, and I'll show you where that's kept. And the queue that I'm going to be listening on is local. So for the portal, I had a queue called portal, and for this local development, I'll have a queue named local. And go ahead and click on create. And that's going to create a template for our function. So this, let me go ahead and build so we get our NuGet packages. So aside from the function that it created for us, it actually also created a local.settings.json. So here's actually where you would have the connection string. So we have a variable called Azure Web Job Storage or property, which contains the connection string. Now, when we configure our function, first off, we have an attribute and it says function name, and this is actually what shows up in the portal. Then you have the trigger type. So in this case, we have a queue trigger. And the first parameter, as you can see, is the name of the queue. So that's local. And now, where is it going to get the connection, the storage connection in this case? Well, it's going to get it from a property called Azure Web Job Storage, and that's what I showed here. So that's the Azure Web Job Storage, and this has it's pointing over to our connection string. And so that's how it knows where to read the messages from. Now, since this is local environment, this is full-on Visual Studio, the nice benefit here is that I get breakpoints. I get the nice debugging experience that we're all familiar with. If I click on Run, what that's going to do is, in a separate window here, let me bring that over. In a separate window here, we have the Azure Functions runtime being executed locally. So this is not a simulator, not an emulator. This is actually the same runtime that Azure uses. So once we are ready to deploy our code, it actually will deploy our code into Azure Azure itself, and this is the runtime that it uses. So you get a very nice consistency between your local development and once you are actually in production in Azure. What I'll do now is we have this function that is configured to read from the local queue in our storage account, and that's what I'm looking at here. So it's the same storage account. I just happen to have a separate queue. I'll add a message. I'll just say test. And remember, I'm doing this in the portal, and the message was added. And as you can see, our function that is running locally saw the fact that there was a message in that queue, and it executed our function. We have a breakpoint configured in that function, so it stopped at that breakpoint, and now we actually can have the traditional rich debugging experience. So if I mouse over a variable, you can see that I have full debugging tools that I'm familiar with. So let me just go ahead and click on continue. And this message should have been consumed, which it has been. And then the output here shows test, because that is what we have in our function here. It just outputted that. So as you can see, this is how you would go about doing local development. So your development is done locally, but is actually interacting with the triggers, which could be in Azure, at least in our case. So let's just say that you're ready to deploy. So what you can do is you could go into your function, right click on that, and go ahead and click on publish. You can then, you have the option of deploying to a consumption plan or the premium plan. And then you also can create a new one here, or you can select an existing one. So I'll go ahead and use an existing one. And again, I'm logged in to my subscription in Azure, so you can see my resource group. And if I expand that, then you'll see that I have that consumption function plan available to me. Click OK, and then I'll create this, and then I can just click on publish, and it'll deploy our code. However, this is not the approach that I would recommend. Instead, I would recommend that you work with a CI/CD system. So obviously there's support here for both Git and also Visual Studio Team Foundation source control. So this you can make use of in Azure DevOps, and that is the approach that I would recommend rather than right-clicking and publishing. However, that is an option, but I would not recommend it. Okay, so that is a demo of doing development locally using Visual Studio 2019 in our case. And now we get into serverless. Now, I think that in order for us to talk about serverless, I think we should talk about the evolution to serverless. If we think back to the dark ages where we had servers that were on premises, back then you were responsible for the hardware, the operating system, the scaling of the application, and the application itself. Then along came the cloud and offered infrastructure as service for the VMs. So no longer were you responsible for the hardware. However, you were still responsible for your operating system, for your app, and for the scaling. Then the other offer from the cloud was platform as a service. So now you actually did not have to worry about either the hardware or the operating system, but you just have to worry about your application and the scaling of your application. And now we have serverless. With serverless, you don't have to worry about the hardware, the operating system, or the scaling. You simply need to worry about your application. So what is serverless? The three tenets for serverless is, the first one is the abstraction of servers. And this is fairly easy to do because the PaaS already takes care of abstracting away the servers. Next, you get event-driven and instant scale. So your function is not always just running, just waiting for someone to make a request. Instead, you get event-driven compute, meaning that whenever there is an event, then you'll go ahead and react. So your function could actually not even be running at all, but when an event happens, it will spin up your function, execute that, and then spin it back down. And then you get instant scale, so that if one instance might not be enough to handle the load of all the requests coming in, you get instant scale, and this is scaling out to additional instances. You pay per use and sub-second billing. So here you're again only paying for when your function is running, and then when it does run, you actually are being charged at a sub-second unit. So in Azure Functions, it goes down to 100 milliseconds. So if your function takes 400 milliseconds, then you'll be charged at the 400 millisecond. That puts us into scaling out. Now, for scaling out in Azure Functions, the unit of scale is the function app. So in our demo, you saw that we had one function app, and in that function app, we had two functions. We had an HTTP triggered function and a queue triggered function. Now, let's say that the queue triggered function is just overwhelmed. There are so many messages coming in that it just cannot keep up. So what you would want to do is you would want another instance of that queue triggered function. Now, if you want to scale out, you actually are going to be scaling out the function app because that is a unit of scale. What that means is that you actually would get something that looks like this. So the HTTP triggered function is also included when you're scaling out because the scale out is at the function app level. If for some reason you only wanted your queue triggered function to scale out, then that's where you probably would put that in its own function app. But so just keep in mind the fact that that is a unit of scale. If your function is hosted in the app service plan, then it is you who will be responsible. First of all, you have to be in the correct service plan. If you're in the basic service plan, what you get is just manual scaling. Essentially, it's a slider where you'll be able to select how many instances of your function app you want, and that's it. However, if you're in standard or premium, you actually do get access to automatic scaling. To configure automatic scaling, you'll need to specify the metric to trigger the scaling by and the threshold. So in this instance here, we have the scale out rule that whenever the average CPU percentage goes above 70%, you would like to increase the instance count by 1. And whenever you have a scaled out rule, make sure you have a scaled in rule so that when traffic lines up, you can actually reduce the instances. So here we have a scaled in rule, which says that whenever the average CPU percentage goes below 40%, then go ahead and decrease the instance count by 1. And at the bottom, we have the instance limit. We have a minimum, a maximum, and a default. The thing to note here is that in the minimum is 1. You cannot go any lower than 1. So you always will have at least one instance of your app service plan running at any one time. Now, the opposite of that would be the consumption plan. And here for the scaling, it's Azure Functions that will take care of monitoring for incoming events and requests. It's actually going to also take a look at the amount of resources that each function is taking or it's making use of. And then it's going to automatically scale out or scale in to provision either additional VMs as required or to remove those additional VMs, and here it can go all the way down to 0. Now, the way that this works is using a scale controller. So you have your function that has subscribed to some kind of event emitter. So in the demo, for instance, we had a queue-triggered function that was subscribed to the storage queue. The scale controller, what it does, it actually is able to monitor that event emitter. So it knows the age of the oldest message. It knows how many messages are in that queue. It knows how long it takes the function to process each of those messages. So using that information, it actually knows if the current number of instances of your function is enough to process the number of messages in that queue. And if it isn't, it actually will then scale out to additional instances. And if it's over provisioned and there are too many instances of your function, it actually will scale back in. So that's one instance of how Azure Functions is able to automatically, without you configuring anything, able to scale out and scale back in. Now, worth noting that a single function app can scale out to a maximum of 200 instances. So for this demo, I'm going to go into the portal and show how we go about configuring scaling out. Here I'm in the portal. And I actually want to show you the fact that I have, let me show this real quick. Going to the resource group, and we'll see that we have two functions here. So the one that we've been working on is this consumption plan, but I actually also have another function, which is an app service plan. We can see that by the fact that it's standard here. So that's a standard plan, the S1 that we took a look at. So the way that we would scale out this function app is we would go into the platform features, we would go then into the app service plan, and then we would scale out. So if this wasn't basic, then all we would have access to is manual scaling. And so this is where we would have to go in and do the scaling ourselves. However, since we're in standard, we can actually do automated scaling. So here we can add a new rule. And the rule is going to be based on CPU percentage, but as you can see, there's quite a number of metrics that you can use to scale. And what we're going to do is we'll say that if the average CPU percentage is greater than 70% for the past 5 minutes, and it is average, go ahead and increase the count by 1 and have a cooldown period of 5 minutes where I don't want you to do any kind of scaling. So I'll go ahead and add that scale out rule. But remember, if you have a scale out rule, make sure to also have a scale in rule. So for this, we'll keep the CPU percentage. And this time though, we'll say when it is less than. In this case, it is let's see, less than, and we'll say 40% for 5 minutes. 5 minutes. We will decrease the count by 1 and with the cooldown period of 5 minutes. Okay, and then we get into the instance limit. So here, let's see what happens if we try 0. So as you can see, this has a requirement of at least 1 instance at any one time. Okay, so that's the difference here. Now let's go ahead and compare that to serverless. So in serverless, this is the function where we have our different, this is a function app where we have our different functions here. But what we want, and you can see here that this function is consumption plan. So let's go ahead and set up scaling for this function. So same thing, platform feature, app service plan. And then if we go into scale out, you'll notice that it actually has that grayed out. And this makes perfect sense because like I mentioned, with serverless, it is actually Azure Functions that's responsible for the scaling out and scaling in of your function, and it is not you who determines that. One thing to note here is the fact that this option of networking is disabled. So that's one limitation that you have. You actually cannot set up a VPN connection between a consumption plan from your function to some kind of network, whereas the in here you actually do get networking. Aside from that, there's very little differences in terms of hosting your function either in consumption plan or the app service plan, and you actually have the access to the same languages, access to the same integration, same triggers. So what we did here in our examples, when we were in the consumption plan, these functions were actually done in the consumption plan. We could have just as easily have done these in the app service plan, and none of the code, none of the integration would have changed. Same thing with the queue triggered function. We would have had access to the storage queue and then being able to write to the blob storage without any kind of limitations that would have been different from a consumption plan or the app service plan. So that's actually the demo that I have for serverless. So as you can see, there's very little in terms of how you develop. It's more the way that your function scales out. That's the big difference here. And now that brings us to a relatively new concept called durable functions. So what durable functions are is essentially a way to orchestrate complex workflows where it would be fairly complicated to do that if you had to do that yourself. So durable functions, what they do is they allow you to have essentially stateful functions using a serverless environment. So durable functions takes care of managing the state, making sure that gets persisted to storage, creating checkpoints, and restarting the function if it ever goes down. So here's a couple of use cases where this makes sense. So the first one is chained functions. That's where one function calls another function, which might call another function. The other one is fan out and fan in. So one function will get the work, and instead of having to do that work all itself, instead it's going to fan that out to multiple functions. So it'll split that work up into small chunks, and it'll give that work out to different functions. The issue here is that when you fan in, meaning that I want to know when I'm done, that actually gets complicated. So there's something where durable functions can make that very, very easy. And then we get human interaction. So say that you had an invoice that you needed an approval. What you can do is you would send out a request for an approval, and if for some reason within 30 days it does not get approved, it will automatically decline it. But at any point in those 30 days, there could be that human interaction where they can approve it. And this is fairly easy to do with durable functions, and it would have been fairly complicated if you were doing this yourself. So let's take a look at what the function chaining would look like if it was to be modeled in a durable function. So we have one function. So function 1 calls function 2, which then calls function 3. And the way that this will be modeled in a durable function is that essentially you're first calling function 1, you're passing in null as a parameter. You then get the result of x. You then pass x to f2, you get y. You pass y to f3, you get z, and you pass z to f4, and that's what you return from this function. So as you can see, this function is relatively easy to read. It's very linear, and the way this is working is that on each await statement, it's actually checkpointing the state, so that if at any point this function were to die and it needs to restart, it actually can rehydrate the state that was saved in storage and then pick up where it left off. One of the requirements for it to do this, though, is that the code that you have here has to be deterministic, meaning that you cannot be making use of, like, for instance, random numbers, because the next time that it picks up, it won't have the same value. So that's one small requirement in order for you to make use of durable functions. And here we have fan out and fan in. Traditionally, you would have a function that is going to load all the work that needs to be processed. So this could have just been a simple query to a database and it gets 100 records. So what this function is going to do is it's going to split up that work amongst 100 different functions, and each one is going to take one of those records. That's not that difficult to do. However, how does that function know when they're all done? That part actually gets pretty complicated, because now each function needs to somehow update some sort of storage mechanism that says, hey, I'm done. And then at the end, this function needs to be polling to see when they're all done. And once they're all done, then do some kind of processing with the results of each of the functions. So this gets pretty complicated, but durable functions actually makes this fairly easy. And the way that it does this, for instance, in this case, we have a list, which is a task of int. And in the line where it's calling F1, that's to mimic where it's getting all of the work that needs to be processed. So that gets stored into the work batch. So let's say that has 100 records. So it's going to loop through those 100 records, and then it's going to create a task for where it's going to be calling F2, and it's going to be passing in each of the items in the work one at a time. So F2 will be called 100 times with each one record. And all these tasks get added into the array called parallel tasks. And when the for loop is done, then it actually will do a task.whenAll. And here it will wait for it to process, for F2 to process all of the work. And once it's done, it actually is able to get the results. And in this case, it then calls F3 with the sum of the results. So it's a little bit more code, but as you can see, I would think it's fairly easy to follow here. And it's a lot easier than if you were to do this yourself. Now, Azure Functions has a way for you to start the call and then check on the status of the job. So here we have a curl command. So in the first curl command, it says here, do some work. And that's what the first line says. The result of that would be a JSON message. And in addition to the JSON message, note that there is a location that's being returned. So in the location, it says you can access this endpoint to get the status of this work. So the second curl command will make a request to that endpoint. And as you can see in the results there, it says that it is currently running. So then if you make another request, you can see that at this point that the result now says completed. And actually the payload here, the JSON result, actually includes also the result of the work. So this is how you're able to have a synchronous status check of your work. So you initially will submit the work, and then you just check on the status of that work. And now we get to pricing. Pricing using an app service plan is fairly straightforward. We have a plan that you'd select, and then you know how much you're going to be paying if you were to run that plan for a month. But the interesting one here is on the consumption plan. So this is a little bit different. So here you are paying per execution. And the way that this works is it will charge you by the number of executions and also the gigabyte seconds. So the gigabyte seconds is how long does something take and how much memory was used. And then here are the prices that you pay. So you pay $20 cents US dollars per 1 million executions and 0.00016 cents per gigabyte second. Now, the nice thing though is that you actually do get a free grant. So per subscription, you get 1 million free executions and you get 400,000 free gigabyte seconds. So now let's take a look at an example of the pricing. Here we have a sample API application. And let's say that we have 10 million requests a month. On average, each request takes half a second to execute and uses half a gig of memory to complete that execution. So let's do some math. So we have 10 million requests times half a second times half a gig per request. So that is 2.5 million gigabyte seconds. As far as what's actually billable, we have 2.5 million gigabyte seconds minus our 400,000 gigabyte seconds, which are free. And that gives us 2.1 million gigabyte seconds. And using that 0.00016, that ends up being 33.60 US dollars. And then for the requests, those are 10 million requests minus the 1 million free grant. We then get 9 million requests that we need to pay for, and that's $1.80. So combined, that's $35.40 that we would be paying for this function if it was hosted using the consumption plan. Now, so let's talk about some of the best practices. So first off, when do you choose one plan over the other? So the app service plan, this is the plan that you would choose if you're planning to run often or continuously. It just makes more financial sense if you're going to be running very often, just host it on the app service plan. Also, if you currently already have, for instance, a mobile app or a web app, which is being hosted in an app service plan, you might have excess capacity where you can deploy your function app onto the same app service plan. And then if you want predetermined costs, so you saw we selected one of the plans, S1, I think that was 73 US dollars per month. And I know how much I'm going to be paying if I am running that for a month. Now, when would you go with the consumption plan? Well, if you have something that's one-off or once in a while, then you would want to go with the consumption plan. So for instance, let's just say that I have a webhook that is in GitHub. So I want to fire this webhook whenever someone does a commit into one of my branches. So I'm not going to create a whole app service plan that's going to cost me $73 a month for some events that might happen a dozen times per month, or if I'm lucky, a couple hundred times per month. It just does not make any sense. For that, it makes more sense to have the consumption plan. Now, one restriction in the consumption plan is the fact that you actually do get a hard 10-minute limit so that your function cannot be running more than 10 minutes. If your function reaches that limit, it actually will be terminated. Now, if your function hits that limit, I actually would argue that Azure Functions is probably not the best platform for you to be running your compute. Instead, I would look at maybe containers or maybe a web job, something else. Azure Functions is really meant for something that is small, that it takes max a couple of seconds. You should not be using Azure Functions for something that takes 10 minutes. The consumption plan should also be used if you don't want to worry about scaling. So you notice that in the app service plan, I had to specify the CPU average and then the threshold of 70%. But what if you don't want to, or what if you don't even know what metric or threshold that you want to scale on? So if you don't want to worry about that, just host it on a consumption plan. And then if you just don't want to pay for an app service plan, like I mentioned, if you have some webhook that's going to fire and trigger your function a couple times per month, you really don't want to pay for a whole app service plan. As for actual best practices, like I mentioned, avoid long-running functions. This is not the platform that you want to be using if you have compute that's going to take minutes to complete. And also use queues to communicate between functions. And that's what I demoed, where we had the portal and the HTTP triggered function. They were all writing messages to the queue. Then we had a queue triggered function that was being executed whenever there were new messages in that function. that Q-triggered function knew nothing about the other functions. So it had very nice, there was a very nice decoupling of our applications. There was an indirect communication and there was no direct communication, meaning that if the Q-triggered function was down, because we added this layer of indirect communication, it did not matter to the HTTP triggered function. It just kept on adding those messages. At some point, that Q triggered function will come back up and it will process those messages. And then we want to write defensive functions. So you want to allow for retry logic. Azure Functions has built-in support when you're working with Service Bus as your trigger, that if it receives a message and then, for instance, you want to process that message by talking to SQL Server, and for some reason there's some kind of transient errors with the communication, you want your function to exit with an exception. Azure Functions is going to see that your function exited with an exception, and it's going to put that message back into the queue, allowing for retry. You don't want to exit that function and say, oh, I couldn't process this message, and then just have the message be removed from the queue. Instead, you want that message to be retried and to see if possibly there's a way for it to actually get processed correctly. And then you want to make use of dead letter queues. So let's say that you do try to reprocess this message multiple times, but you know what? It's just not helping. So at that point, you want to put that message into a dead letter queue so you know that there was a message that was not able to be processed. The big takeaway, I think, for Azure Functions is how it's all about abstracting. Serverless abstracts away the compute, and then the triggers and bindings abstract away the services that you integrate with. No need for you to write all that boilerplate code in order for you to integrate with a third party. No need for you to learn SDKs. You simply wire up using the triggers and bindings, and then you just work on your business code and not have to worry about all the other SDKs. So you let Azure Functions take care of that for you. And that brings us to the end. Hopefully you found this interesting. Hopefully you learned something from this presentation. And here's the different places where you can find me online. Until next time, thank you.